in listen-only mode.
Good afternoon and welcome to this webinar. What I would first of all like to do is welcome you from different parts of the world. My name is Bob Willis and I'll be presenting today's webinar with a special guest star from India. Now, before we start talking about solder preforms, I'd first like to introduce you to the control panel, which you have on your screen at this moment in time. Now, the control panel allows you to do a few things during the presentation. First of all, you can open and close the control panel by clicking on the orange button. This prevents it obscuring your view of the slides during the presentation. You can click on the full screen view. This again gives you the best view of the slides during the presentation, or if you're in a conference room with one or two other people, then of course on your projection facility this will give you the best view of the slides. Now, at any time during the webinar this afternoon you can ask a question. All you need to do is type it directly into the control panel as indicated here by the red arrow. Now, the questions will be answered at the end of the session when both myself and my special guest, Graham, finish their presentation. So anytime you can type up a question directly into the control panel and we'll look at those questions at the end of the session. Now, if you have any technical problems during the webinar, please use one of the telephone numbers provided on your registration and reminder emails. You'll also need your webinar ID number and access code, which was included on your emails. It's not possible for the presenter or his assistant in this live presentation to assist you online. One thing to bear in mind that at this moment in time, the internet is under considerable pressure. So it may be that you have an issue locally in your area or possibly even in your factory if everybody's watching football or some other sporting event. So if you have a problem, just log in again. That's the best way, and it will be the quickest way to get back to the presentation. At the end of the webinar this afternoon, we have a couple of survey questions. And basically it relates to the content of the webinar, things you'd like to hear about in the future, and giving a score for us, the presenters. Hopefully you just take a few moments to fill that in. You will be receiving a copy of all of the slides shortly after the end of the webinar, and they'll be sent to you by email. If you don't receive them, please check in your junk file. That's quite often the place it actually ends up for some unknown reason. If you want to watch the recording, you can watch that on my own YouTube channel, and it will be available shortly also from the Indian website as well. Now, this is a charity event, and I don't want to push this, but it is a charity event, and I really would be pleased if any of you would like to contribute just a small amount of money for this webinar, specifically directly to the charity. And I've provided the link so you can donate directly to the charity. This is the second charity event I've done, and hopefully it's been successful for those two charities. So again, if you'd like to participate, like to donate, really would appreciate it. Now, my guest speaker is Graham Wilson, and he'll be joining us a little bit later on to talk about preforms, the more advanced preform technologies, and some of the aspects that I am not going to mention during my presentation. And Graham has been with the company quite a few years now and is a very practical engineer. So we're looking forward to his presentation as well. A little bit about my background just before I start. I've been involved in electronic manufacturing all of my working life. I guess I'm close to retirement, theoretically. I still love doing training presentations, hands-on events, and all these sort of things that I've been doing over many years. I've written a couple of books. I've produced 20 training videos, interactive CD-ROMs, and a variety of other training medium. So that's basically a little bit about me, my background, and where I've been involved in electronic manufacture. I'll talk a little bit more about it as we go through the presentation. So first of all, what is a preform? Well, if you look at some definitions, everybody talks about a solder preform, but a preform can be other materials, as Graham will mention a little bit later on. But generally speaking, preforms, when we talk about them, we're talking about solder preforms using traditional alloys that have been well used in our industry for many, many years. But what a company, a supplier will do is specifically design a preform for an application. So the benefit there is you get a consistent volume of material for the particular operation that you're trying to conduct. And one of the nice things about many of the suppliers of preforms in the industry, they support with a good design service, and also they have a wealth of experience and normally a wealth of sample types that they can show you to illustrate a point. The other thing about preforms is it's not something you necessarily immediately think of to solve a soldering solution. But if you have a soldering problem, it's something to look at, and where it's not mainstream, it may be the solution for you, but it may also be a way of overcoming some specific problem that you have in manufacture. And hopefully we'll illustrate this during this preform webinar. So in terms of packaging, well, again, if we're looking for small volume, packaging is kind of less important as long as it protects the preform. It doesn't allow it to degrade during storage. But if we're talking about automation, if we're talking about hundreds of thousands of joints or interconnections, then packaging must be considered and is just as important as the preform itself to enable us to assemble them effectively and cost effectively in manufacture. So in this illustration, I show tape and reel feed, tape feed, bulk, samples in a glass container, and just separator sheets used in a protective packaging format. So it very much depends on the volume, the automation you're going to be using, and of course the material itself. Now, preforming or preforms is generally an older technology, and it's something that I did in fact grow up with as a junior engineer and a production operator many years ago. So we use this technology in certain aspects, and I'll give you a couple of examples of that. There are different techniques to manufacture preforms. Some are very simple methods and some quite complex methods because of the structure of now the newer forms of preforms, which we'll discuss in the second part of this presentation. I've already mentioned the guaranteed solder volume. One of the unique things about this is we've got a lump of metal and we can define the volume. So consequently, if everything else remains the same, i.e. the area that we're trying to bond, then the volume of solder should be consistent. We can assemble preforms manually, and there's a lot of companies do this, and in sort of medium to high volume. But really, when we're talking about high volume, we really need to look at methods of automating the process. Potentially, preforms come pre-fluxed, flux loaded, or they can be used without flux, and you're using those preforms in an environment which provides a fluxing atmosphere to clean the surfaces we're going to bond, and also providing the medium by which the solder flows across the surface. Some connectors and some other components you can purchase which actually come with preforms pre-mounted, and most of those examples really come about because of pin-in-hole intrusive reflow, something that some of you will know that I have a great affinity for. So first of all, feed-through examples. Now, I used to assemble feed-through parts for RF circuits, for space applications, and also on connectors. And on these, for our types of military products that we used to produce at GEC Marconi, these were all relatively simple preforms. So we could control the volume of solder, we could reflow it with hot gas, or we could reflow it in vapor phase successfully and get consistent yield and performance. Again, it was a manual process, manual separation of parts and loading to the PCB prior to the assembly process. But nevertheless, if it was designed correctly, it would work very effectively. Now, back in the day, I used to make my own preforms. Now, I'm not unique. This is an example of somebody producing preforms. And basically what I'm doing is wrapping wire, cord wire around a metal rod. And the benefit of that is very quick to do, very cost effective to do, but you do get a lot of inconsistencies. And if you look closely at the samples, what you tend to do is get some burring at the point of cutting through. And also what tends to happen when you've got lots of little half circles or C's, they tend to link together. So when you lift them or separate them out to use them, unfortunately what tends to do, you tend to bend some other parts, which then again reduces the quality that you're going to get. If you look at supplier samples from suppliers, you can see on the right hand side of the slide here that they've been cut through, but they haven't separated. So they are preforms, they are produced in a similar way, a unique way to the specific company, but again they're sealed and they're not going to link together, which can be a disadvantage when you're looking at higher volumes. Now, a good friend of mine who has retired but seems to know everything about soldering, and I've known him for many, many years, actually told me that back in the day, companies used to use knitting needles to define size. Now, whether this is true or not, and I would not disbelieve him, this just gives you an idea of sizing. However, I used to use anything which was appropriate at that particular time. But of course, if quality engineers were around, I would always say I was using a calibrated steel whole gauge set to calibrate my samples. But that's for small volume and manual production. Now, when we went to telecom products, or when my company went to telecom products, we were in competition with 3 major companies in the UK, all producing for the telecom market. It was a vast market. And all of those 3 companies were basically producing products, backplane products for interconnection, and all of them were using wire wrap. And wire wrap is a method of producing an electrical connection with no solder joint, but a low resistance. So there would be no resistance change on this interconnection method, even though we weren't soldering points of wire to terminations. And basically this process worked by wrapping wires around a square pin. So you can see here the wire is indenting into the wire surface of the pin. So if you look at this particular area and then this microsection, and then go closer into this microsection, you can see how the corner of the pin has indented into the wire. What this did is gave us a gas-tight joint. And this has proven extremely reliable and still continues to do that for companies using wire wrap. But there was a lot of debate in the industry about, whether you needed pins and wires which were square with sharp corners and they didn't have any solder on. If you actually had pins with solder on, yes, the indentation may be less, but the pull-off force, the actual pull-off force by which we would qualify a process and test a process would really not be affected. In fact, it would be a higher pull-off force. If you did contact resistance, you wouldn't see any difference. And even after environmental testing, temperature cycling and aging, you really wouldn't see a difference. So this is one of the ways in which our company went in a slightly different direction to 2 of our competitors back in the day. So back to the preforms for a moment, because that's what we're talking about today. There is lots of different methods of getting preforms onto connectors. And of course, it comes down to an engineer figuring out what the most effective way of doing it. And the way in which we started production on our backplane assemblies was having a tooling plate with recesses in, and we would literally sweep the preforms into the recesses as you see here. So just imagine a pallet, like a solder pallet if you like, with lots of little holes in. We would fill up those holes with preforms, and then what we would do is lower the connector into the preform through the pallet, and then flip it upside down, and then we would run this through vapor phase. Now, vapor phase was a popular method of soldering for this type of technology of backplanes, using this type of technique, because the vapor phase fluid would not be trapped in the connector, it would all drain out, it would give consistent reflow, all of the sort of benefits of the traditional vapor phase process. So reflow would take place, we would have beautiful solder joints, but the point of it is you do not have solder on the wire spills. So when you're doing wire wrapping, it was perceived at the time that you got better results. Now, we went away from this process because it was so expensive. And what we did is wave solder. So we actually had a specific machine with a very deep wave designed with Electrovert at that time, an UltraPack, and we would wave solder all our backplanes. As you see examples on the photograph on the left-hand side, some backplanes, some small backplanes. Those were made up into much larger frames during the assembly process. And again, you can see a historical, this is not me only having a black and white camera at the time, the pins coming out of the wave. This was part of our evaluation trials. The disadvantage of this process is you've got to maintain your wave solder machine pretty much on spec, and also you mustn't have flags. And these are an example of some flags from my process. If you have flags, you can't wire wrap, and certainly not automatically. However, if you manage to wire wrap and there wasn't any flags, the results are pretty good. So this is just an alternative to a process that we first went to because everybody else was, but we felt that we could do it more cost effectively. The alternative to that process, as I'm sure all of you now know, is using press fit connectors, which really is the process of choice today. Now, another technique we used to use with preforms is heat shrink sleeving. And this is an example of a modern heat shrink sleeve incorporating a solder preform. And what you're looking at now in video, it just shows the solder reflowing, bringing together the multi-stranded cables, reflowing, and some suppliers of these sleeves have a colouring agent which change colour when reflow has taken place or a certain temperature is actually reached. These are very elegant today. Our preforms that we used were not quite as elegant as this, but fundamentally they worked exactly the same and proved to be extremely reliable as a process. Another preform that we used back in the day, and I did some work with Nokia, and this is sort of going back in the mist of time, using rework and preforms for this. This is an example of a very early preform, and you can see here that we've got solder preforms, but there is a change in the shape where the square shape is actually defined, and we'll illustrate why this is a little bit later on in a video. But basically the idea here is we're trying to join together multiple deposits of solder, but what we want is them to reflow, but before they can actually move and wick to another termination, which we don't want to happen, is the small reductions in dimension between the individual deposits will break first. So that's a controlling factor. In my work originally with this preform and others, it wasn't as successful as I'd hoped. So what we went on to do is use preforms in a slightly different way, but you could consider this to be a preform in that we've got solder spheres held in a paper-like material. And this is for reballing on BGA packages. So basically what we did is we took this, we loaded the BGA into the frame, which was already pre-fluxed. Then there's a clip which holds it in place against the ball spheres, and it goes through either vapor phase or convection reflow to reball the packages. I'm not a lover of reballing, not necessarily from a reliability or production, it's just a pain. And it's something I'd always subcontract to a company, and there are 3 companies in the world which do it much better than I could ever do it. But again, just an example of a preform type application. So preforms, as I've suggested, come in a number of different flavors. There are preforms which are not coated. There are preforms which are flux coated by the supplier, and there are preforms which have got flux laminated within the structure of the preform. Again, depending on the method the supplier uses to produce these particular parts. And both of them can work successfully, and those that are not flux equally can work successfully if you get the right combination of materials and, of course, soldering parameters as well, which we'll come on to. More recently, one supplier has offered preforms which have got nickel balls embedded in the preform, and the idea here is to control the separation distance between the two parts to be soldered. So it's kind of like a standoff, if you like. There are some other advantages of having something within the bulk of the solder, which Graham will mention a little bit later on in his presentation. One of the other forms which has become available is preform support. You know, some sort of support mechanism, not balls in this particular case, so a structure within the preform, again to control the standoff and standoff separation of the parts. And again, one of the types will be mentioned by Graham a little bit later on. So in terms of fluxes, now there's not going to be the same range of fluxes that we know about from flux manufacturers, paste manufacturers, etc. in the industry just for preforms, but there is quite a range that is available. So again, if you're a no clean company, if you're a clean company, you've got the materials available to you. And we're talking about very small percentages of flux, certainly nothing like when we consider the amount of flux or flux vehicle that's present in a solder paste. So the actual residues left behind are fairly minimal in most material cases. But again, that's something you speak to your supplier about and evaluate it for its cleaning and cleaning potential. So in terms of placement, well, from manual, tweezers, vacuum tools, again, works perfectly well. For very small preforms, if we're looking at quite complex shapes and very thin shapes, then you've got to look at how you support those, because if you deform them, particularly if you were looking for something to place onto a BGA pattern, then that might be very difficult to do. Automated pick and place, well, it's fair to say that in the last sort of 5 or 6 years, possibly even longer, there's been a lot of interest in the use of solder bricks, and I use that term, so I'm non-commercial, I'm not using commercial terms, but basically we're talking about a lump of solder which we're putting into or around a joint, and that's predominantly to improve the performance for pin and hole intrusive reflow. Again, you've got to consider automation, how you're going to automate the process, but in terms of the solder bricks, they're normally in tape and reel feed, and a variety of different sizes are available, and they specifically can solve a design problem quite often, and that's one of the advantages of that technique. We have feeder mechanisms, vibratory feeders and locator plates, which are available from different suppliers. But you've got to make sure you pick the right material and also think about what other aspects of the process you need to control, which we'll mention as we go through. This is just an example just of a production line where I was running 4 different types of connectors on boards. So we were stencil printing, we were assembling these particular connectors to the board, along with BGA and all the other sexy components as well, at a live demonstration. And on some of these parts, I was using preforms to increase the volume of solder to specific joints. So I could actually demonstrate the difference between using it just with screen printed paste and non-screen printed paste. If you get the design right of your board and get the hole to lead ratio right, it's not difficult to produce joints to IPC. But if you've got that extra flexibility of using solder bricks to overcome old designs where somebody doesn't want to change the hole sizes, which isn't difficult to do, then it's a great solution. So in terms of feeders, as I said, tape and reel, vibratory feeders, and of course more complex preforms in some form of waffle tray. A couple of things: vibratory feeders, they can change or affect the dimensions of the preforms. So be aware of that. And it's continual vibration. If you're getting moving parts and they're sitting in there for hours, so it's important to make sure, if you are considering that route, to look at preforms and the feeder mechanisms and see how they sense the amount of parts that are in the feeder and the final feeder tube prior to pickup. But if they're just going around and round and round for hours, they will damage it. They will remove flux from the surface. Also, with shiny solder-like surfaces, you need to look at vision systems if you're going to be placing complex preforms onto a surface. Not an insurmountable problem, but it's just something to bear in mind. Now, in addition, in Asia, there is 2 suppliers who actually make feeder mechanisms which are basically cut and form. So they take cord wire, cut and form it to a shape. So you're putting a fluxed core wire directly onto the solder paste to overcome the volume. The slight disadvantage here, if you were going along that route, is you're obviously adding more flux to the joint, but then again, you could always use non-cord wire in this type of application if that was something which was appropriate to you. Now, in terms of reflow, we have the norm, convection, vapor phase. We also have conduction and induction for reflow of solder joints. And again, it very much depends on what sort of volume we're talking about. But if we talk about the fundamentals, we're still talking about temperature profiling. And if I just give you this simple example, we've got a board, we've got some hot spots and cold spots and warm spots. But if you look at connectors, you will tend to always find with any connector, the pins at the outside of the connector or the ends of the connector will get hotter quicker, and the ones in the middle and in the middle of a group of connector pins and ones that are also close to the body of the connector will be colder. So just think about that when you're doing profiling, and you'll find the hottest and coldest parts of the printed circuit board in that particular case. That's kind of different to what we would do with traditional profiling. But in terms of traditional profiling, we do it in exactly the same way by mounting thermocouples to the printed circuit board, ideally by soldering. That is the best performance you'll get from measuring a profile. If you're hampered or you're have to look at soldering RF shields or metal shields to your boards for some particular reason, then again, that will certainly have an impact on the temperature on the board. As indicated here by the orange on the edge, it will have an effect in that area, and certainly it will have an effect where I've shown the blue circle. So that will be a colder part. So again, you've got to look at the structure of your printed circuit board, and then you're trying to meet the requirements of paste manufacturer. You're also trying to guarantee you do not exceed the recommendations of the component manufacturer, because if you do either of those two things, you may not have a successful and reliable product. Now, just one thing I wanted to just chuck in, because I'd seen this just recently on some frames that I was soldering. This is some examples of slight de-wetting but more outgassing. One thing to bear in mind, that all tin surfaces are not necessarily going to solder really, really well and effectively. Yes, they should do, but also look for those surfaces outgassing. A lot of people forget that plating can outgas and cause pimples and voids on surfaces, just like a solder joint. So don't always blame the materials. Quite often it can still be other surfaces which have an impact. It really is a cosmetic issue, but when you look at it for the very first time, it's not very attractive on these heat shields. So to produce a solder joint, well, we take our board, or we take our substrate, our component, our metal frame, whatever that might be. We place our preform, which may be fluxed, may not be fluxed, depending on the solder joint we're actually going to be producing, and of course the alloy we're going to be using. And then we place our other surface on top. And slowly what we're going to do is heat up that whole structure, and depending on the flux technology we're using, the solder technology, if it's tin lead technology or if it's lead-free technology, there'll be a reaction with the fluxing material to aid the soldering operation for whatever surfaces we're going to be working with. But if you're looking at more exotic materials, or you're looking at stainless steels or covars, different materials which historically can be more difficult to solder, then we may now have to look at a slightly different direction. But slowly, when we get up to reflow temperature, if it's tin lead or if it's lead free, the solder will become a liquid, and in that liquid phase we'll start to form a solder joint, which will obviously incorporate intermetallics across the surface. Now those intermetallics will be different depending on the materials you're joining, but if we're just talking about solder, it's copper and tin. Those are the two mediums that are joining together. On some occasions when we're soldering to nickel gold, it's tin nickel, because that's what we're actually soldering and forming the joint. And if we look at the surfaces, as I've mentioned earlier, there's a whole myriad of different surfaces that we might be soldering to. And you still need to think about these surfaces, aging of these surfaces, and how solderable they are if you're using preforms or not using preforms. The fundamentals of soldering, if we're making a solder joint, do not change. So there's just a list of the materials that potentially we could be soldering to. And the intermetallic formed, as you see in this microsection. The structure and shape of the intermetallic will of course depend on the metallurgy and of course the time and temperature that is in a liquid state. So in terms of other types of soldering, induction soldering may be new to some companies, but basically what we're creating is a magnetic field which heats the joints within that field. And that's an example of solder connections being made to a three-dimensional plastic board. So a connector with pins, the preforms are placed over the top, they're flux preforms, and reflow is created. In this example, we're looking at three different connectors, and these RF connectors are being soldered using induction. You can see the solder preform reflowing, and the nice thing here is you can see the inspection hole. Some of you will be familiar with this if you're familiar with norm soldering of connectors or crimp connectors, etc. You can see the solder reflowing and actually being visible in the inspection hole, which is kind of nice. It gives you a good warm feeling. And this is an example of de-wetting or non-wetting, where the solder is clearly reflowed, but this is not a preform issue or a soldering issue. This is a soldering issue with the connector. So either the mass didn't get up to the right temperature, or alternatively, there's a wettability problem with the surface of the plating on this particular example. But back to preforms again, and this defined and design that has to come into creating a preform for your particular application. Here you can see a connector, some preforms, and you can see how the size is defined, obviously for the volume, but also the interconnections have been designed to break during the soldering operation to make sure we're not robbing or stealing solder from one particular position to another. So that's a good example. On the other hand, this is an old example back in the day. Again, I was running in sort of, I think, early 90s, and these are preforms with no design really. There's a hole, there's a square lump of solder, but the interconnection to them is the same dimension, same thickness. So we all know that when you reflow solder joints, they do not all reflow at the same time. So consequently, some will reflow before others. That's the reality of reflow soldering. So if you haven't designed in these automatic brakes, these fuses if you like, then what can happen is you can rob solder from one pin to another. So this is not a very good example of a preform, but it's a good example of illustrating what can happen. So on the left-hand side, you can see three perfect joints. Everybody's happy. On the right-hand side, you can see two joints, one which is lean and one which is like the three joints on the right-hand side, sorry, on the left-hand side. I personally would say both of those joints, whether it be lean or normal, if you like, are perfectly okay. They're never going to fail in a month of Sundays, but it's not consistent. So if we're looking for consistency and auditability, being able to inspect automatically, you don't want to refine your process to have this amount of variability in it. You want to improve it. So again, Preforms correctly designed can do that. Now this example just illustrates what I've been talking about. So we've got a preform, we've got a couple of examples where I've illustrated the points, and if you watch the video clip, what you'll be able to see is just me reflowing on just a pad that I had available, and you can see the break. It's quite clear, and that's what we want to happen. So the volume of solder stays where you want it on the particular connection that you've actually placed it onto. So these are nice examples of what I call engineered preforms. Just briefly, if you're new to pin-in-hole intrusive reflow, and if you want a book on the subject, it's free to download. I wrote it a couple of years back, and it covers everything on pin-in-hole intrusive reflow. It also includes the use of solder bricks as well. Now on to components. There are components available. These are 3 suppliers that I'm aware of that developed connectors with added solder. So these could be used where you're using solder paste, or depending on the volume and the size of the holes, they may have sufficient volume to fill the hole and give you your joint without using solder paste. Personally, I've always used solder paste with these types of applications, and that's what I would do anyway. I would also say that I would tend to look at the design first of all and see if I can modify the hole sizes to improve on hole fill generally in the examples that you see, or the example that you see. So on to bricks. This is the basic process, and these are 6 images that I've taken from one of my video clips showing this process in operation. And what you're looking at is the solder bricks are being placed onto the solder paste, and slowly during reflow what will happen is the solder paste will become a liquid, the brick will become a liquid, and slowly be drawn into the joint to give you the volume required. So the 2 video clips you're watching at the moment illustrate this particular process. So what you can see is solder paste becoming liquid, and you see the brick slowly being drawn into the volume of the joint quite nicely, and very, very obvious that we've got a bigger volume on some pins than the others because we've used the bricks, and that's why we can see those present on the surface. Just a couple of examples of other types of preform reflowing, and I just wanted to allow you to see what's actually happening rather than actually making a joint on this occasion. So basically I'm just reflowing a pin with a donut. This is going to reflow, and you'll see the solder wet the pin, and of course what in this particular case the solder is wetting, it would form a joint within the barrel of the hole if that's what you're trying to do. But equally, depending on the atmosphere you used, the amount of wettability, the amount of drawing away of the solder from the bulk of the joint area could also be controlled. So if you were working in nitrogen and you were getting too much of the solder drawn away from a surface, then you just turn down the nitrogen level or beef up the air content, and that would reduce the wetting. Second example, again just using the Doughnut as an example. So here's a pin, it's in a printed circuit board. There was one Doughnut there. This is a flux laminated preform, and we can just see reflow taking place. There is sufficient solder here to fill that plated through hole, and again there's no contamination to the rest of the pin assembly. Now, as many of you know, over the last few years there's been problems with void formation and voids in QFNs, and personally I tend to find the majority of that is not necessarily process related, design related. A lot of it is vias and via hole gassing, which I see so often in manufacture. So it's not the paste, it's not the profile, it's quite often something else. And also, one of the other things I must say is that there are a lot of applications for QFN bottom termination components which don't need the heat dissipation capability of the pad in the first place. So concern about voids in certain applications are really not an issue at all. Again, where we're talking about high demand and high heat output from a device that's got to be dissipated, absolutely, that is an issue. So if there is another technique that can reduce that problem on those particular parts and can overcome issues on the board, the vias, via gassing as well, then that is something really of interest. So in this particular example, it's just a video clip just to show you what's happening in the process. So these are just two QFNs with preforms in place. You can see this outer solder joints reflowing. Also, you can see the preform reflow on the surface of the pad. And again, with the design rules and recommendations which are available from suppliers, they'll be able to recommend the thickness of the preform for a particular application. So if you were using paste with the preform, or if you wanted to go on a different route, then they could recommend the standoff height and thickness to accommodate your particular requirements. So that's just a couple of nice examples. My final example, again, is a pretty typical example from on connectors, on housings, etc., where we're actually forming a seal, a cavity seal. So on this example, we've got an enclosure. It's got metallized surfaces where we're going to actually make a solder joint. And basically what we would take is our lid, our preform, we'd place our preform onto the surface, place our lid onto that surface, and depending on the preform material, because remember I said that there's a whole range of materials out there for different applications which are based on the requirement of the sealing, the temperature requirement of the product, etc. So it's not just traditional solders which are used with preform technology. And this is kind of a nice point to remind you about any questions. If you've got any questions, please type them directly into the control panel, and both Graham and myself will do our best to answer those questions for you. It's now my pleasure to introduce our next speaker, and my guest speaker of the afternoon is Graham, and Graham Wilson's there, ready, poised to start his presentation. Graham. Graham, it's over to you. You self-muted. I'll try and... There you are. There you are. You're away, Graham.
Thank you very much. Yeah, I'll have to reboot my start there. So the control tower had me on mute as well, I think, there. So it's my pleasure to be with you this afternoon, Bob, albeit remotely from the countryside in England. Usually we find each other in these trade shows, but this is exceptional circumstances. So thank you for your presentation thus far. I'm Graham Wilson from Indian Corporation, but I'll just give you a little bit more background to some of the preform technology, engineered solders technology that we can share, and go through some applications, and as Bob said previously, some novel, more modern interconnects as we move forward. So I'll take you through basics of a solder paste, but then we'll go through the non-traditional alloys that are available from the industry as well to suit many different requirements out there, be it mechanical or thermal. We'll go through some more geometries and some flux coating, as Bob previously mentioned, but then we'll take you to the interesting stuff with the different verticals and some application types where preforms, engineered solders, and these newer types of engineered solders are used. As Bob has previously said, preform technology is not new. Metal shaping and forming has been done for even before the concept of the photograph, and I think this possibly is one of the earliest photographs of blacksmithing, but I didn't pick it up from Bob. So, but thankfully the technologies have moved on, manufacturing techniques, and the situations where preforms are needed definitely has moved on as well. Briefly bringing you back into the realms of maybe solder paste that lots of the audience are familiar with. So solder paste in itself is a more modern way of making the interconnection between the PCBA and a component. In this case, a solder paste is roughly 50% by volume a flux system, which is used as the medium to contain the solder powder or the solder volume. These are usually blended together to make a convenient paste that you can then take through a stencil print process. Positives, it's great for mass manufacture and application. Potentially negatives in some applications. Flux residues are not required in the application, or a flux residue would actually contaminate the surface of a component in play, so such as a die surface or hermeticity of a seal, for instance, and maybe even blocking out the function of that device. So the benefit of the preform that we would have in its place would be that the fluxing volume that could be required, as Bob has said, based on the way in which you're reflowing or the need of the application, would be reduced because you are now at practically 100% metal. Okay, so you've negated that potential contaminant within your application you're going to build. The engineered solder forms that we are seeing inside the market now can be many different geometries, from very simple solid shapes to arrays, as you can see in the picture in the top left here, from the split rings that Bob showed earlier on in his presentation. Spheres definitely have a place in the market for controlling the solder volume. And we have a few other special forms that we're able to offer that have specific tasks for thermal transfer or component standoff height or bond line control, and the interconnections as Bob showed on his presentation before. But here we are at the engineering side. We have tens of thousands of options. If you could practically dream it up, potentially it could be a solder form. To reconfirm the benefits, as Bob has previously said here, I've mentioned the lower fluxing levels. This could be a benefit in the application process. Bob has previously mentioned the controlling of the solder volume. So this improves your repeatability of the solder joint you're trying to make, which improves the quality by nature. Having a solid metal piece beneath a component, such as the QFN, you could reduce your void levels if you were having problems with flux entrapment. And again, we can introduce step soldering processes. This would be where you have multiple levels of your assembly sequence, and you need to have a different soldering temperature. So you could move from a high lead alloy, which would be in the region of 300 degrees Celsius, then move down to a second operation. But now, since 2006, the traditional SAC solders. And then further down, you could come again to tin lead at the lower melt point that you would traditionally have used before lead-free. And then beneath that, you can go all the way down to the tin bismuth alloys, and even lower to the indium tin alloys as well, that are around about 120 degrees Celsius. All of these, of course, can be packaged, as Bob's shown, for various manufacturing volumes that can be from hand assemblies to automation. Here's a quick graphic here showing a multitude of alloys. And we're here at Indium Corporation. We are manufacturing alloys from the liquid stage. So we're using alloys that remain liquid at room temperature, right the way through to the gold containing and some braze alloys here that are in excess of 280 degrees Celsius. So if there is a potential need for a step solder, I'm sure there's an option of an alloy in the market out there. Just to assist you, we have resources that are available online, and quite as an engineer myself, I like this interactive table. It helps me talk to yourselves, the customers, when we're trying to define a particular alloy need, be it for the liquidus temperatures or some of the known other properties like electrical conductivities through to the shear strengths as well and tensile strengths. As Bob has mentioned before, the engineered solder preform or preform is a solid geometry. And here you can see on the right hand side, if you are adding the topical flux on the outside, this is following the red line here as represented between two surfaces that are intended to be soldered. We are following the IPC classifications here for soldering flux coatings, and these are assessed in the following strengths based on the need of the application. Just to give you an idea here, that of the outside, you can see in the bottom left-hand corner, this is possibly a vintage vehicle that's needed an automotive headlight lamp pin hardwiring into the shell of the reflector. You can see here the control of the volume would be important just to get that repeatability even in the manufacturing stage. You see on the outside the flux coating, and then of course it moves and gets the repeatable volume on that automotive headlamp. Another opportunity here you're seeing is a washer, and there's two Doughnut washers here that have been flux coated. This is a microscopic view of a fiber optic ferrule coming from the right hand side that's being reflowed by hot air. And you can see here the difference in the outer circumference of the ferrule into the interior socket. The solder will reflow and it capillary fills into those recesses, making that nice fillet you can see. So here these are able to be controlled and packaged, as Bob said, by many different ways, so you can handle them as your manufacturing sequence allows. Just take a deeper dive into the verticals. From this side, we have been making preforms pretty much since day one, since 1934, so in excess of the 80 years. So if there's an application that needed to be soldered, it probably was soldered with a preform at some stage in its life. So we have thousands of things we could possibly talk about, but we try and break them into these verticals by today's definitions. So we'll take a look further at some of the common ones, but I'm sure if you have the time and energy, we can talk about some of the miscellaneous ones offline and some of those from the past as well. Let's begin with PCBA. So Bob called these solder chunks or solder bricks or solder pieces. These are now, to maintain the volume of these deposits here, these forms, we are mirroring the sizes of passive components, so such as your resistors or capacitors. Now these make it infinitely easy for people to understand the volumes and then understand the handling of these devices. And as Bob has shown previously, they have a multitude of uses in the industry. And they are what I would consider as an engineer a get out of jail free card, especially if you were a contractor and you needed to meet a defined solder volume and the stencil just wasn't of the right geometry, so you didn't have the same solder paste, but you could then add a solder here, we call them fortifications, solder brick, to the application to increase that volume. Here on the left-hand side here, you can see that the benefit is here we can have the stencil thickness from the solder paste deposit. There's a uniform height, so we don't have to consider the rules for step stencils. So we can have the clearances desired. We don't have to make that factor coming in there, so we don't have unintentional wear on our stencil print process. This is a USB connector that's on the side of a board. It's also going to have a lot of interaction in its life, so it's going to have a lot of plugging in, plugging out. We need to add the additional solder volume here as a mechanical feature, just to stop that wear and tear on that connector, causing a open circuit in the lifetime of that particular piece of equipment, making it a little bit more robust in its application. And you can see the difference in the volume by represented to the left of the red X, and then to the left of the with Preform. You can see that the solder indicator there, which is the punched out recess, you can see the solder well has been filled and it's now bonding to the top side of that connector. Now, I must now admit that Bob's videos were much more impressive than myself's, but I'm sure I won't be the last co-presenter or guest to say such a thing. Here you can see an Indian corporation video on the right-hand side of a through-hole dip process connector, and you can see the solder brick has been added to each of those solder paste deposits, and as the video goes up, you can see that solder brick going into those connectors as it reflows down through the board. Looking at the cross section of this device, you can see the benefit of adding that solder, because the fillet in the barrel in here in the top picture on the right hand side is not showing a fillet. Then when we look to the bottom side, you can see the fillet's been formed not only on the top side of the circuit there, but actually on the bottom side as well, so providing the good process indicators that quality inspectors are looking for. Moving forward to the QFN examples that Bob showed, again with fantastic videos, thank you Bob. But here is a little bit of the benefits of the design features, because not all manufacturers out in the market are giving the design guidance as to which preform is desired underneath. But I would echo what Bob was saying. I would make a review of the component TDS to find out the thermal demand and to find out if your PCB has been designed with a traditional LAN pattern or one that's been designed for the component. In cases where the solder paste is not enough, or there is an entrapment of a flux residue, or the design requires more solder volume because your component is now possibly not even a device that is a flat terminating or a bottom terminated device. It could be a J-lead package or a gull package that now has an underbody that has been now exposed for thermal transfer, but that naturally is not interfacing directly with the PCBA. So there's a standoff that needs to be filled with the solder volume. And again, the stencil printing techniques and the step stencils may not accommodate those design features. So the addition of the solder preform, again, with or without a flux, depending on the process, can be increasing the solder volume as desired. We can see evidence of this on the bottom here, looking from a power amplification type of device. And you can see, reviewing the bottom termination by X-ray, you can see there is on the bottom slide here in the central picture, you can review voiding in the X-ray. With the addition of the solder preform, you can see it's a different contrast, but there is lesser voiding that's apparent by using the 100% metal preform. If I move us along into the review of the power market, it's quite a wide market as we move forward into various different electrical controls and demands that are coming into the industry with the decline of fossil fuels and the need for electrical driven vehicles, from trains, trams, some energy recovery circuits now are coming in from even aircraft, military or commercial as well. So there's lots of different applications that now are being changed in their design requirements, from the mission statements or the mission profiles, from the designs where the combustion engine was used or the traditional die was used. Everybody is now, the world needs more power, so the power densities are now increasing as well. So therefore the mission profiles are changing, and potentially the traditional soldering interconnections are not able to provide the reliability to those new mission profiles. In such cases, here for illustrated in this case, we have a preform here that we are calling inform, and here this has an added structure inside the solder, which is not collapsible in the soldering process. So this defines a standoff height over the area of the soldering connection. The defined height, or the bond line control, that allows us to limit the tilt that a potential component or a substrate could have against its next level, in this case showing a base plate. If the solder is thinner, as it's shown on the left-hand side, any thermal excursion or thermal cycle that's applied would be adding more stress and load into that particular area. If you're able to control the bond line thickness, as in the bottom reference, you can provide an even thickness of solder or a minimum thickness of solder, so that you can have a defined planarity between the levels. This, of course, would give the even stress relief over the area. This, of course, then allows for improved thermal transfer, but also we are able to prove that against the use of a standard preform or a standard solder paste, where the tilt could be an issue in the production, we have minimum 2 times the reliabilities in most thermal cycle cases. So this could be in excess of 3,500 cycles, where the pass-fail criteria in aviation was as low as 1,000 cycles. So we're able to improve that reliability to this assembly, and in turn improves the reliability of the component or module in service as well. This technology is available for larger areas, such as the substrate to baseplate attaches, but is also being used now at the next level in power module manufacture between the die and the substrate as well. So we have different combinations of the matrix that can be used that would provide differing levels of bond line control. As it is a technology that is directly in replacement to a preform, it allows itself to be dropped into the existing manufacturing flow of a facility that's already using preforms. So there's a low cost of ownership for adding into that technology. We see that in this technology, the added matrix doesn't add any increased levels of voiding that may appear in those interconnections. Just jumping into the thermal areas, we have alloys and preforms that are available that have a good thermal conductivity, bulk thermal conductivity. Being we called indium corporation, that material actually is indium, pure indium in this case. So we have engineered a structured preform. We call this heat spring, but it is a textured pattern device that allows for improved contacts to non-planar surfaces or non-coplanar surfaces. So the material itself has a high bulk thermal conductivity of 86 watts per meter Kelvin, which is massive in terms of metals. But with this, indium itself is a compliant ductile material, so it's easy to shape. So if you've not had the pleasure of touching or experiencing indium, the material, it's as very much as ductile as a Play-Doh or plasticine. So if you push your finger against it, it would leave an impression. Similar to, you can see the impression of the logo in the indium foil on the bottom right-hand corner. It's this ability to be malleable and impressionable that when you clamp it between two surfaces that need to be joined and a high thermal transfer needs to be given between those, that the peaks would flatten where there's a close contact. This just increases the surface area of contact, which gets you a better thermal conductivity. We can see that as we are a solid metal, we are not suffering the characteristics that can be seen for other thermal materials in the market. So we're not going to be drying out. We're not able to be moved by any deflection in the applications. So you can see here, if I show you on the right-hand side, you can see this is a thermal map here. There's 16 thermocouples that have been measuring the temperature. And if you imagine just looking at this, the green is a lower temperature, and the pretty much like hopefully on the weather maps today, the sun shining and you get into the hot zones, you're looking for red. But in this case, a red zone is a hot zone and could be indicative of the non-operation of your device much further as it gets too hot and maybe suffers thermal runaway. If we watch the graphs, you'll see a subtle change, and you'll see this moving from a time zero plot right now through to 1,000 cycles here. And you can see the change is happening. And actually the energy that's been given by the thermal cycle has actually improved the areas of contact of the indium. And you can see actually getting a lower temperature after that initial burn-in cycle. This property of the relaxing of the material is showing that the material is creeping. So this is a metallic property. And again, you can see from a different cycling on the right-hand side here, that even as you go further, the effect of that temperature is giving you more problems with the non-metal materials. Let's move on to a little bit of a different application set that's slightly away from electronics, so medical devices. So we'll be talking about devices that are used invasively inside the body for procedures. and some of those that are left in the body as a permanent fixture. I hope everybody on the call has no need for these, but if you do, I hope they're very reliable for your foreseeable future. So we find that the preforms can be used in many different areas of these, from mechanical attribute or an electrical attribute, or as Bob has mentioned previously, we do see that some of the applications are used for hermeticity as well. Just to give you an idea, we mentioned earlier on in the presentation alloys that have a high temperature. Here, gold tin, but we're not using the gold tin here for a high temperature withstand, and these are cochlear devices and implants, but these are used to seal feed-throughs to allow the electronics to talk to the body but not interfere with any of the environments coming into contact with the electronics. This is an application of a catheter, and here you can see on the top the wire on the left hand side, the nitinol wire, and then you can see the stainless steel being joined. You can see on the bottom picture, if the resolution is good for you, just at the point where you can't focus, where the glow is on the bottom picture, you can see this is the joining area of these two materials. So this can be handled by a gold tin alloy or another alloy, depending on the requirements of the application. These alloys are joining here, especially to the stainless steel, they have different levels of oxidation or harder oxides on the surface. So these will require slightly different fluxes that are used in the PCBA. These fluxes will be stronger, more acid-based, and will need some sort of cleansing afterwards to remove them from the application. To help you along with these types of new challenges as they're presented to you, we have applications research kits, and here is a specific one for nitinol, which comes with a couple of sections of materials that can be used, the flux and the appropriate metals of joining. And you can see here it's not only on the stent materials but also in the catheter, but these are similar material sets that are used inside these arenas for inside body procedures. This slide may be a little bit older now, but this was cutting edge technology when the photograph was probably taken. But this is a component attaching here using a very small washer here. So we're talking here 25 thou. So we're talking, this is a very, very ultra small washer here. So we're talking, 0.6 of a millimeter around. Unless you are a James Bond villain or in the banks in London right now, gold is a good topic, but it's actually used in electronics markets as well, medical, and high-end communications, and it's used for hermetic sealing with flux-less soldering operations, as was mentioned before on the presentation. These are devices such as optical measurement systems that are looking down on us on Earth, or providing star mapping as well. So these are devices that need lenses sealing over the top of them so that they can see out as well. With the gold-based alloys, these are available in all the forms that we mentioned before, from a solid wire, even a solder paste, but we can also make them into the preforms that are used for sealing devices, packages that were shown on the presentation before. Similar schematic here, where you have a device lid going over the top of a circuit board, or in cases of actually putting a die onto a plated area in a package or on a buzz bar, depending what you're manufacturing. And also the preform could be used in sealing on a lens cover to one of these optical processor devices that we've seen in the market as well. With indium, there's the properties that we mentioned previously. So the alloy is in the middle temperature bandwidth here of the processes. So it's 157 degrees Celsius melting temperature for pure indium, but also the alloys with different materials and can be as low as 118 degrees Celsius for reflow soldering. But if you added in some gallium, of course, you could then make it into a liquid alloy for special applications. But here we'll talk about the ductility that the material indium would have. Not only does it have this ductility at ambient temperatures, room temperatures, or somewhat elevated temperatures until it reaches liquidus, it maintains this characteristic into very low temperatures, such as the cryogenic temperature ranges. So it's perfect for making a seal for a very cold gas, a cryogenic gas or liquid, for those applications. Here on the right hand side, you can see it's actually just been using to seal a lens. But in the following application, again, it's in a semi-high pressure application where it's been used to seal to as a gasket operation, so sealing two bits of hardware together. We can see that the shape form can be in a traditional washer format, or it could be, as illustrated before, it could be tied wrapped as a cylinder, so a solid wire. It's very easy to form, so it could be made that way. And on the right hand side at the top, you can see that somebody has made their own gasket material, possibly as an emergency measure or possibly by design, but they've actually twisted in indium wire around the circumference of that device, and you can see the tail of this wire just hanging off on this side. So once they're wrapped together, the indium itself would be compressed between the applications, and indium would actually self-wet to these two mating surfaces, and it's those self-wetting properties of the oxides that are wetting onto the surfaces that would perform this airtight or gas tight or liquid tight seal as required. We mentioned earlier on in Bob's presentation, again with a fantastic video, an array of washers connected together with an integrated tie bar. And again, these applications are shared in ways that Bob has mentioned before for connectors, so making it very easy to make a multi-pin out connector very repeatable in a process. We see these being used in many verticals at the moment, but we see them used in military avionics where these multiple array connectors are used. Again, looking back to Bob's past for solder feed-throughs, you can see this connector here has got a multitude, and also there's a ferrite bead standing up in this grouping assembly here as a filter on this connector type as well. Again, you can see a couple of automotive examples now using a flex circuit in this case, that's then joined and placed into an overmold with a connector on there as well. So this, using the flex connector, this could be used with many different alloys. It could be used from the SAC alloys right the way down to the lower temperatures, depending on the characteristic of the flex circuit, but could be using tin bismuth as well. And again, on the right-hand side, you can see slightly different way of manufacturing an automotive connector. Here you can see there's an embedded connector. Then there probably would be some filling of a dielectric gel as an insulative measure for the connector. Maybe it's used in harsh environments. to meet its mission profile. And then you can see the lid placed on the top side of there for a mechanical reinforcement. Bob showed a good example of the interconnection between two wire wraps, two wire pinouts here, so two pieces of wire. You may see them in your cast area, you might see them in lots of wiring from any different places, but these would automatically come together, and this sort of tube here would be in the center of these two insulative plastics. And as Bob showed on his video, you would see that this solder would then be of a lower temperature potentially, so that it didn't make the plastic melt completely, but it's the plastic would shrink with the hot air applied to it, and the solder would reflow, guaranteeing the mechanical connection as long as the insulative connection onto the bare wire as well. It's a good time to mention the research kits. I touched upon one earlier on in the presentation. We have many different engineering kits that can help you triage a situation or learn about a particular property of an alloy. So there are many different combinations that you can have. I love them. They're great as an engineering toolbox. So we have those specifically set up for different application sectors, but they are somewhat configurable as well to different contents should you be desired. Coming back to the packaging, it's not very good to manufacture such technical products and then send them in a package that necessarily isn't holding them in the correct manner or the correct way in which you want to interface them into your production. So we would always have a conversation, and we can address any packaging you need to guarantee that it interfaces to your production, or the preform would get you in good shape. This could be as simple as what we call a black box, but has nothing to do with aircraft tracking here, or the waffle trays that Bob showed as well. So depending on the application that you really have. So we have a low to medium type of idea of where we want to go with your production. Or if you're into high volume, of course, we can move to larger waffle trays or specific tray packaging as you desire. But we could also do the tape and reel processes that would interface to regular pick and place or die handlers as you would like them to. As is best, if you would like to get into contact with us, we can have a discussion on the application needs, and we can discuss its mission profile so that we can help you diagnose or determine which alloy would be suitable for your application. We have tools and crib sheets that can be found on indium.com, and they can help the dialogue between us. Just allow me to just say thank you to Bob for the opportunity here to be part of his charity webinar. Thank you very much. And from Indium Corporation side, we have future webinars, as I'm sure Bob has some excellent content planned in the future as well. So thank you very much, Bob, for the opportunity.
Well, thank you very much, Graham, and excellent presentation. And it's just nice. There's a few things there that I was thinking about as you went through your presentation, particularly the excellent example of SOICs. You know, some of the high operating voltages of some, they do have those thermal relief pads underneath. Most people think what the hell they're there for, but anyway. But that standoff height is quite a significant gap you've got to fill. So, you know, your example about using using a preform in that example is absolutely perfect. So that was a nice example. It's interesting that yesterday I was taking a PC apart, and I found a very, very high speed processor, and they'd actually used preforms to solder that in place. So you know, you come up or find these things all the time, which is good. Right, just a reminder before we get on to questions, while we're all here, if you have the opportunity, please, if you'd like to make a small donation to one of the charities, this is just 2 charities we've selected for this particular webinar. Really appreciate if you would just take a couple of moments and make a small donation. That would be really, really good. I really appreciate that. So if you've got any questions, all you need to do is type them directly into the control panel, as we discussed earlier. We've had a few questions in, so we've got a number of things for Graham to answer. And he won't have seen these, but I'll go through those. Just a reminder, if you're interested, I obviously run webinars every month, as I do for a number of other organizations. My own webinars are listed here, so if you're interested in any of these topics, or of course we do our video on demand service, webinar on demand service for topics that you might need, but you don't actually see listed. So again, lots of opportunities for support and education within the industry. Okay, so back to questions. If you've got a question, please just type it directly into the control panel, as some of you have already done, and Graham will do his best to answer them. Well, I will just answer 2 questions first of all. Yes, you will be getting a copy of the presentation slides as PDFs. They will be sent out directly after the end of the webinar. Please look in your junk box if you don't receive them, because that's 99% of the time. If you don't receive them, that's where they're actually sitting. So I'm sorry you're going to have to clear out your junk box occasionally and have a look. But that will be sent out. And of course, the video recording, which a number of other people have asked about, will be available directly, well, I mean, within about sort of 30, 40 minutes at the end of this presentation on my YouTube channel. And of course, it will be available on Indium's archive of their many webinars in a few days' time, I would assume. Okay, first question, is it preferred to use preforms of the same alloy? So if we're making a solder joint, is it preferred to use preforms of the same alloy?
Hi, yeah, in this case, I would always recommend having, if you're interfacing a preform into a solder joint, I would stick with the same alloy, because then you don't have any other intermetallic phases or any interactions that could change the melting temperature or the mechanical property of the solder. So yeah, long answer, but short answer is yes, stick with the same alloy.
I would totally agree, and let's for a moment forget about the metallurgy, let's forget about the reliability. If you've got to argue the case that no, we're not using exactly the same alloy with a customer, and then his customer's customer or the quality engineer, or if you've got some failures, then it's not a nice place to try and talk yourself out of. So if you possibly humanly can, use the same alloy. It just makes sense.
Yeah, okay. I totally agree. You would definitely avoid the debate of moving from a tin lead to a tin lead silver or a 305 to a 387.
Yeah, it's just a little bit more of this and a little less of that. Okay, what application does not require fluxing when using preforms, or what is the requirement? A process change if you don't want to use fluxed preforms.
Generally, I would say you need a flux or a flux reaction happening with the atmosphere you're going to use. There are a couple of applications in the market where you have no ability to use a flux or a reflow fluxing atmosphere. In those cases, you would have to use the cleanest of gold, noble surfaces that wouldn't have any oxide present onto the surface. And then be reflowing in a no oxide environment, such as a nitrogen, or even if you could, a straight up vacuum, but gold to gold and as clean as possible.
Okay, thank you very much for that. Next question. If I want to use a particular preform in my SMT process and I can't get it with a flux, how can I add the flux?
I'm assuming you can't actually add this into the overprinted area of a solder paste, so it's not going to get drawn in the answer. So that would be one solution. You could use a naked preform or alloy only, then place it into the solder paste deposit. There would be sufficient flux to make sure that that alloy was drawn in, as the video showed. If you couldn't use a flux into a solder paste, potentially you could use a deposit of a tacky flux or a gel flux, or you could even, in a low mix manufacturing sequence, perhaps you could even, dip your flux onto your preform before you start.
Okay, this is a slightly longer question, so let me just read that. Is there any limit on vacuum level that can be reached while using indium for soldering? I have RF components that must keep very low vacuum. Are there any experiences in soldering such devices? So that's a good question.
Yeah, and that's quite a technical question that I don't have the technical answer for, but I do know amongst the customers that we keep, we have applications similar, and indium is able to be used as long as the design considerations for making that seal have been accounted for.
I mean, the bottom line is, provided the components are not too expensive, take a bunch of them and try it out, and see what the capability is. Obviously, a supplier of components is going to work at the widest specification he can to protect himself and the component, and sometimes you have to evaluate the components. I mean, one of the things I find, in manufacturing, whether it's cleaning boards or any of the processes, sometimes there isn't the information available, and you'll find it very difficult to get the component manufacturer to actually, put it in writing. You have to do some trials, and that's the bottom line. If you look at examples of components warpage, we know the component warps, but engineers have to mess around with the stencils and put bigger blobs of solder paste in certain areas to overcome the warpage. That's an example where we've got to deal with the situation. And that's not ideal, but that's what engineering's all about, I'm afraid. Trying to solve the insurmountable problem. Okay, next question. When solder the rectangle preform to a substrate, always seeing the original boundary of the. Oh, okay. So basically, he's still seeing the shape of the preform visible. Is this a problem?
I'm not sure I understand the concept. So if you place the preform, therefore then it melts and retracts, but you're still seeing the original impression?
I think what he is inferring is that he's still seeing part of the original shape. I mean, bottom line for me, it hasn't reflowed properly. I mean, I've seen components that have been produced, or connectors which have had pins connected to them, and they've reflowed, made a beautiful joint within the barrel of the hole where the pin went, but on the top where the original part of the original preform was, it hasn't completely reflowed. So it takes up the shape, kind of misshapen shape of a preform.
Yeah, could be that situation, or thinking about it, it could be that the preform's laid onto the top surface of the PCB and had some sort of impression left on the resist there. That's just from the process.
Yeah, I mean, equally, obviously, if you have too long a time at prior to reflow with solder bricks in pin and paste, you're going to exhaust the flux, and the flux is needed to some level to allow complete reflow of the brick. So those two, it's a process. It seems like more like a process issue, I would say.
I would say that if the impression is not causing you any interactions, and again is meeting the quality standard of the solder joint, it could be just an indicator. Okay.
This is a gentleman who actually sent us an email or put on the registration form that he had a problem with tin bismuth silver preforms, and I did ask him to send in photographs, but unfortunately he probably hasn't had the opportunity to do that. So I'll ask you the question, but it would have been nice to see specifically what he's talking about. So the question is how to reduce solder balls when using bismuth tin silver preforms. I haven't really experienced this as an issue, but I don't know if you have.
No, I've not seen it much of an issue, but I don't think the temperature banding could have an interest in the solder balls or beading here. It could be mechanics of the reflow profile, depending on whatever they're doing.
Yeah, I mean, it's not specific.
It's difficult to assess without a photo, but it could be that the process is slightly too low, or it could be an interaction to the solder resist again, where the solder isn't allowed to coalesce in such a way, or it could be just the volume is too great and there's an overspill based on the design of the PCB.
Okay.
But please be in touch. Let us have the photo and we'll have a discussion. No problem.
Yeah, as I would say, a picture's worth 1,000 words and a video is worth 1,000,000 words. Right, another question. Oh, it's just about the recording. Yeah, the recording will be available either on the Indian past webinar section of the website or in the next sort of 50 minutes, 60 minutes on my own YouTube channel. So if there's any other questions, we're down to the end. Any final questions? We'll just take 2 more questions before I let Graham get on with his next meeting. So any other questions you would like to ask, just type them directly into the control panel. So generally speaking, you know, when you first got into the world of preforms, Graham, what did you think?
Honestly, my history is electronics is very similar to yours, Bob. So I've been in this game a little bit longer. But I've been with Indium now 13 years, and when I first joined, I was pretty much only using solder paste at the manufacturer I was with, and yeah, substituting this and coming into the wild world of preforms where there's thousands of opportunities and applications, it's mind-blowing. But it's very, very interesting as an engineer to see these diverse applications, and especially all of these diverse and different alloys with their properties as well. So yeah, keeps me very engaged in the market. But when I first came in, it was a little bit overawed.
Okay. All right. Well, thank you very much for that. I'd like to thank you for participating in this charity webinar, Graham. It's really been a pleasure. Enjoyed playing, and hopefully you'll have a wonderful afternoon or move on to the next meeting. Thank you very much. And to all of the attendees this afternoon, thank you very much. A reminder, you will be receiving a copy of the presentation slides in PDF format. You will see the copy of the recording, if you wish, on my YouTube channel, and hopefully you'll join us for another webinar in the not too distant future. Once again, thank you very much, and good afternoon. Good afternoon to you all.